summarize last time. So we started with the one-dimensional solution. So I had asked whether to try this dimer problem, to set up the transfer matrix for the dimer problem. Did somebody try? Or anyone? So the question was to solve the dimer problem using a transfer matrix, and also to solve it using a combinatorial method, and asked whether match or not. Did it match? Or did it was any suggestions how to go about writing the transfer matrix for 1D dimer? So why don't you try for 1 minute? You should be able to write. Sorry? No, you have to put a weight Z also for the fugacity. So what is your the size of the transfer matrix? 2 cross 2, 3 cross 3, what? 2 cross 2, and what are the entries? Z, root Z, root Z, 1. Okay, so I can't. How did you write this down? Okay, let me find the eigenvalues of this, then I will know the answer. So Z minus lambda, 1 minus lambda minus Z equals 0. Am I right? This cannot be right. It's definitely not right. So lambda equal to 1. So equal to 0. So lambda equal to 0 or lambda equals 1 by 1. No, this is not right. If I expand this, I get negative numbers. Right? If I expand this, I get 1 minus Z plus Z square. Okay. So, any other suggestions? Huh? Okay. Okay, 1 Z Z 0. Okay. So let me write down a little bit. So suppose 1, 2, 3, 4, 5, 6, 1, 2, 3. I want to write down the partition function for 6 sides. So I have two options. In the leftmost side, I can leave it empty, or I can put a dimer like that. These are the only things I can do. This comes with the weight Z. So if I write ZL, so this is empty. What is remaining is 5 of them, Z of L minus 1. Then I have a factor Z here, and I have 4 remaining z of L minus 2. So if I define a vector like this is equal to something multiplying so it is 1 z 1 0. So this is my transfer matrix. What is it? Is it what you said? Is this what you said? Okay. So if you find the eigenvalues of this, you'll be able to find the solution. Okay. So let me just give one more step. So we have 2 eigenvalues here, lambda 1 and lambda 2. So the solution will be ZL is C1 in general, and you fix C1 and C2 from small l with the boundary conditions that Z of 0 is 1 and Z of 1 is 1. Okay, that fixes C1 and C2. Okay, so that is the solution. So you get some answer which is in terms of small z. What about, so now I want to do the other count. I want to ask how many ways of putting n dimers in L sites. How can I do that? So I want to ask, I want a number. L factorial by? No, what is the answer you said? L factorial, n factorial, L minus 2n. Okay, so let us try L equal to 4. L equal to 4, L equal to 2, let us try. So this is 2 factorial by 1 factorial, 2 minus 2n factorial. If I put n equal to 1, I get 2 as the answer, which is not right. Right? If I put L equal to 2, n equal to 1, I get 2, but I have only one way of putting. So that answer is not right. L minus n factorial. Okay, so can you tell how you got this? Okay, fine. So if you take a particular dimer configuration, so there is some empty sites, some occupied sites, and so on. Think of these as particles of size 2. So number of particles is n. The number of holes is L minus 2n. You want to arrange them, arrange them. So that is L minus n factorial by n factorial, L minus 2n. Because that's the answer. Once you arrange these particles, you expand them into 2. Okay, think of them as single big particle. You expand them into 2, which is the answer which I gave. So now you have to make sure that the answer you get from this one is the answer you get from this one. But the ensembles are different. If I take log of this, what do I get? If I take, this is my some number counting. If I take the log of that, entropy, okay. If I take the log of this one, what do I get? So some free energy, grand canonical free energy or something like that. So you have to go from one to the other to compare the answers and make sure that they're the same. Either transform from here to that one or transform from there to here using a Legendre transform, and the answer should match. So that you should check. So that was the D equal to 1. Then we did low temperature expansion. Okay, so let me try to understand, suppose this was not dimer but k-mer. Each one occupies k size, not k equal to 2 is dimer. How will this answer change? You understood the question. The question is I can now generalize this to rod of length k, and then I ask this commutative number. If you have understood this counting, you should be able to tell that in fast. So L minus Nk by Nk, by L minus plus N, factorial by L minus Nk. So that's the commutative count for that one. Okay, now the low temperature expansion, that's the next thing we did. So what was the idea? At T equal to 0, things are ordered. If I look at T slightly greater than 0, the picture looks something like this. You have mostly plus and a few minuses sitting here and there. So what you want to do is to sum over these small islands as a perturbation series, which we did for Ising model for a few terms. And what we got was Z. So let me write down 2 beta Nj plus something. The small parameter was e to the minus 2k. K is j times beta. This was the small parameter. Okay. So what's the next thing we did? The high temperature expansion. Here, the whole thing depended on this expansion e to the power ks. K into 1 plus t. Where t is our small parameter, tan hyperbolic k. When temperature is large, k is small, beta is small. And then the expansion took the form z is 2 to the power n cos hyperbolic beta j into sum over all possible graphs which have closed polygons with the constraint that each side should have either 2 or 4 bonds coming out of that, and t to the power perimeter of G. So this was our expansion. So what we should do is to, this is in general true, of course this was once we made it, this particular expansion in 2-dimensional Hartree polygons of the kind I described. Suppose I do in 1 dimension, what graphs come? Suppose I take one, suppose I do this expansion. So what is my, so let me write on Z in a way, the sum over S1, S2 up to Sn, 1 plus T times product over Ij, 1 plus T times Si. So this was my expansion. So if you have understood this expansion, what should the answer be in 1 dimension? What are the graphs? Okay, there are only 2 graphs which are, no. So let me look at the open chain. Suppose you look at the open chain, what graphs are possible? Okay, is there any closed loop I can create in 1 dimension if it is an open chain? I cannot. So the only contribution is 1, and you get cos hyperbolic k, which was the answer you got the solution. If I took the closed chain, Then I get two graphs. One is no bond, and the other one is all the bonds occupied. In which case I get tan hyperbolic, and I get cos h plus sin h, which is the solution we got again. Suppose I take the Cayley tree, and I do high temperature expansion for that. What graphs contribute? No connection. There are no loops, so no connection, which implies cos hyperbolic Kn. But we did get a transition in the first day's calculation. What went wrong? So our partition function is the 1D partition function, but that was not what we got in that problem. So the high temperature expansion gives an answer which is not consistent with the results we got. So that you have to figure out why. Okay. So so what is the point? That point is over. So when you expanded this, we got this expansion which was z is 2 to the power. Is the question clear? On the Bethe lattice, there are no loops. So the only graph that will contribute is 1. Okay. So what is the answer we got? Yeah. So Z high temperature expansion. N into 1 plus N plus so on. And if you compare this expansion with the low temperature expansion, which was here, if you replace e to the minus 2k with t, this is the identification we made. If e to the minus 2k goes to t, then the two expansions look similar. So we were at this point, and then we said that this expansion, if it has a singular point, that should match with the singular point of that one. And therefore, we got the critical point to be e to the minus 2 kc is equal to tan hyperbolic kc, giving kc equals log 1 plus root 2. So what I'd like to do first is to just make this connection a bit more. So this connection we made by just looking at the terms. So let's make it a bit more formal. So identify graph by graph that they match with each other. Okay, so how will we do that? So are there any questions before I go ahead? Everything is clear. Okay, so let us take an example of a graph of the low temperature expansion. So I will draw, so let me make some way of drawing the diagram. So I have one upturned spin. This I will draw as one side. Every spin that is upturned, so pointing down, I'll put as a red dot. Okay. And the other ones I'll put as white dots. So we have a lattice like this. And the unmatched, the plus minus bonds, I'll draw with yellow lines. So there's yellow line here, yellow line here, yellow line here. So this was the lowest energy perturbation. So the next one was two of them like this. These were my bonds, which were 1, 2, 3, 4, 5, 6. So what one has to do is to show that for corresponding to each graph here, there's a graph in my high temperature expansion. And for each graph in the high temperature expansion, there is one low temperature expansion. So this mapping we'll just do by example. So here, if I draw one bond, blue line, perpendicular to every yellow line, if I draw a blue line, I get a curve, a square in the on like this. Here, I get a rectangle like that. So so they connect sides which are not in the original lattice, but in the midpoints. In the midpoints of the what is on what is called a dual lattice. So if any lattice is given, if I take the bonds and draw the perpendiculars to them and join them, you get the dual lattice. So this lives in the dual lattice here, and this also lives in the dual lattice. If I take a square lattice, the dual lattice itself is a square. But if I take a triangular lattice, what's the dual of that? Do you know? So if I take a honeycomb lattice, for example, I need few more drawn. It's a honeycomb lattice. I take these centers. So if I look at the yellows, they form a triangular lattice. So if I take a honeycomb lattice, the dual is a triangular lattice. But luckily for the square lattice, the dual is the square itself. So for every particular expansion, every term in the low temperature expansion, I get a particular graph in the dual lattice. And if I give you a graph in the dual lattice, you can convince yourself you'll get one graph in the original lattice. Both are, the allowed graphs. So that you have to convince yourself. So therefore, it says that so this particular expansion, for every term in the expansion here, is a term in the dual lattice that's there. But the dual lattice happens to be a square lattice. Therefore, the KC is the same. But if I had done an expansion for the honeycomb lattice, then my dual lattice expansion is on a triangular lattice, which is not the same model. The model is the same, the lattice is different, the cases are different. But what it does is it relates the critical temperature of one lattice to the critical temperature in the other lattice at another lattice. So unless you have one more relation, you cannot solve. But it happens you can solve, but right now you cannot solve. Okay, that was a very fast. So what I plan today is to look at. Okay, so what you should read is to ask if I take an Ising model in 3 dimension and construct an expansion low temperature and high temperature, they don't match. But you can ask if I take the low temperature expansion and I create the corresponding dual lattice, what does it correspond to in the dual problem? There is some nice Ising model that comes there. Just not the original Ising model, but something else. So you should try to read that up. Okay, so that is a reading assignment for you. So I don't know. Why don't you first construct yourself, and then I'll give you a source. So you ask. Suppose I take the low temperature expansion Ising model in 3 dimensions, and I want to ask what model does it correspond to the dual lattice. You try to construct that, and then we can check for next time. A reference for that. Okay, so I thought this duality we can just do. Here when we did the expansion for low temperature Ising model and we took it on the dual lattice, it turned out to be an Ising model in the dual lattice, the same model. But if you take do the low temperature and high temperature expansion for Ising model in 3 dimensions, there's no such mapping. But you can now ask if I look at the low temperature expansion for the Ising model, and for each graph you can construct some sort of interaction, the expansion for the dual lattice. You can ask what is the Ising model, not Ising model. What is the model for which that expansion corresponds to? Okay, so I thought we should, since we have done this a few times, we should do this for one more model and try to derive the TC for one more well-known model, which is the POTS model. Okay. So let me just briefly tell you what the POTS model is and the phenomenology. They have to try first. So in next 10 to 20 minutes, let's do the POTS model duality to show that you can get the TC of quite a few models this way. So what is the POTS model? So POTS model. So that you have to tell me, no? You have to tell me. You said there are no loops. The POTS model. So the Hamiltonian, let me define, sum over all possible nearest neighbor. So there's a spin variable at each side. Now we can take value 1, 2, up to q. So this is the q state POTS model. Whenever two neighboring spins are aligned, the energy is decreased by a factor of j, by j. Otherwise, it is 0. So this model is one way of generalizing Ising model. There are other ways of generalizing too, but this is more than 2. So this problem also, if you look at low temperature, what's the low temperature? At t equal to 0, what is my phase? Yeah, it is, you can pick up one of the spins and all of them are that spin. So there's a q state, q-fold degeneracy for that. The high temperature is again disordered. So there could be a transition in between, and there is a transition between at finite temperature between a ordered phase and a disordered phase. It turns out that in d equal to 2, there is a continuous transition for q equal to 2, 3, 4. And in 3 dimension, it is first order for, well, first order for all, except for q equal to 2, all the others. Okay. So what we like to do is to do the 2-dimensional case exactly as we did for Ising model and find out the TC for POTS model. Q equal to 2 is the Ising model. Yes. If I put q equal to 2, we have to s equal to 1 or 2. But when they're aligned, it is minus j. When they are not aligned, it is 0. So if I want to get the same answer, I should put j to 2j. If I put j by 2 in my original differential Ising model, I should get back this. Oh, no, it is first order. This is continuous for q equal to 2, 3, 4 only. Otherwise, first order. Okay. So what we'll do is we'll write down a few terms in the low temperature expansion, two terms in the high temperature expansion, and see do they match or not. That's the first thing. So low temperature. So like before, the lowest, the ground state E0 is all spins aligned. How many bonds are there? There are 2n. Each one gives you an energy minus j. Okay. What's my first excited state? It is one spin upturned, one spin not, okay. So there are all spins pointing, well, I should write 1, 1, 1, 1, 1, 1, 1, 2, 1. One of them is not 1, it is q, not q. M, where M can take value 1 to q, 2 to q minus 1. So energy is, so delta E, I lose 4 bonds, 1, 2, 3, 4. These 4 are unsatisfied. So delta E is 4J, and number of ways of doing this is n into q minus 1. N for which spin I change, q minus 1 for the how many ways can I change it. So my partition function is 2nk q times into 1 plus to the power 4k. What's the next term? Is there one? It just is there an argument for that? Well, random theories always give you first order for Q3 onwards. 3 onwards. That's correct in 3-dimensional. Yeah. But why? What's the next term? Now we have done few times. What's the next term? You have to change 2 spins. Which 2 spins? Neighboring spins, faraway spins? Neighboring spins. Okay, so next diagram is the neighboring spin. But are they the same? So now I have, okay, so I'll show 1, 1, 1, 1. I put M1. Should I put them same or different? The same is better because I say 1 bond here. So 1, 2, 3, 4, 5, 6. There are 6 of them. So delta E is 6 times J. Number of ways of doing it is 2n into q minus 1. Okay, so let me write, I'll 2n into q minus 1, 6k. What's the next possible energy? We'll do just one more. What's the next possible? Sorry? I make it M1 and M2. So I introduce one more here. So delta E becomes 7J. But how many ways can I do this? Q minus 1 into, so number is equal to n into, is there factor 2? Or there's no factor of 2? When you count, you have to count correctly. It is just not enough to say it is almost that. Is it 2n into q minus 1 q minus 2 or 2? So let me write, I don't know. 7k plus something. You can put the first one in q minus 1 ways, second one in q minus 2. I'll always go right, q minus 2 ways, but up and down. That is fine. Sorry? So there is one unmatched bond here. No, J. In the past, every bond costs J. Yeah, but since the Hamiltonian of this form is either minus J or 0. In the icing, it is minus J or plus J, therefore the 2J. Okay, so we have derived a few terms here. Now, let us try to do a few terms in the high temperature expansion. First of all, we have to check whether if our duality argument is right, they should match. Only if it matches, we are able to show that one is the other. Sorry? Minus? Yeah, sorry. So the e to the power minus k is our small parameter here. So the high temperature expansion will do exactly the same as we did for icing model. So the term that comes is e to the power k delta Si S1 S2. This is the form that comes. There are many terms, but what we did was we expanded this in the denominator. That's what we did to Ising model. Let's do the same for this one too. So this we can write as A plus B delta Si S1 S2. If I expand it as a series in delta S1 S2, I can only have one term, because delta S1 S2 square is same as delta S1 S2. What is A? A has to be e to the power, when delta S1 S2 is 0, this is 1. And when delta S1 S2 is 1, is e to the power k. So this is plus. Okay. So my partition function becomes sum over all possible S1, S2, and so on. Product over all possible bonds, 1 plus delta S1, S2. This is the straightforward high temperature expansion one can do. So as before, there are, how many bonds are there? 2n bonds are there. Therefore, in this expansion, there are 2 to the power 2n terms. Either you choose one from each term or this one, the second one from each term. So let us call, since t is small, t is large, k is small, e to the power k minus 1 is a small parameter. So let us call this as t, just like before. T. But now when I expand, so order t to the power 0 is easy to compute. None of these terms come. I have 1, but each S1, S2 I have to give a factor q. So this is q to the power n. Right? Now, what is order t to the power 1? Is there order t to the power 1? So that is where 1t comes. So before we had S1, S2 coming here, which we said when you sum over S1 goes to 0. But here now when I sum over, I can have one term which is e to the power minus k minus 1 delta S1, S2 for example. Sum over S1, S2, there's no problem. It doesn't give you 0. It gives you q. Q e to the power k minus 1. Correct? So now there is no way of getting polygons and so on. If I were to draw a line for each delta S1, S2, any possible configuration is allowed. I get a non-zero answer. But let us go ahead with that. So if I draw one particular bond, 1 e to the power 0, I get q into e to the power k, let me call this t. Q into t. The remaining spins give you a factor of q. That's q to the power n minus 2. Correct? I'm summing over S1 and S2. The remaining, there are n minus 2 spins. They give you a factor q to the power n minus 2. So overall, I get q to the power n minus 1 times t. Am I right? Is this, I have to check, that doesn't sound correct. Oh, it seems okay. Is that okay? None of the graphs are eliminated. So now let me look at it at a particular, at a random graph, a generic graph. So is it clear when I say graph? So whenever I choose the term delta S1 SI I'll put a line on the square lattice. So now every term in the expansion corresponds to a graph on the two-dimensional lattice. So if I take a particular graph, so let me take a graph like that. Sum over delta If this is S, delta, this delta function, this delta function, this delta function. So what happens if so this particular graph breaks up into clusters. This has two clusters, unconnected clusters. So when I look at this product over a particular cluster, so let me take this cluster. I'll call it S1, S2, S3. What does it contribute to in this product? It contributes T delta S1, S2, delta S1. No, delta S2, delta T square. There are two bonds, T square, delta S1, S2, delta S2, S3. And I have to sum over S1, S2, S3. When I sum over S3, it gives you 1. S2 gives you 1. But S1 gives you Q. So it gives you Q times T square. Okay. If I do for any other cluster too, the same thing happens. All the spins get summed over except one spin. So for each cluster, I get Q. And for each cluster, I get Q times T to the power number of bonds. Okay. So if I were to write this partition function now, I get Z is sum over all possible graphs, Q to the power number of clusters, T to the power number of bonds. Is it correct? No, if I had a single cluster here, it contributes a factor Q times number of bonds in them. This one contributes Q times TQ. If I had n clusters, it will contribute Q to the power NC, number of clusters. Oh, so cluster, I should say. Cluster is a set of unconnected, cluster set of connected bonds. This is a cluster and this is a cluster. Of course, each single spin also contributes a cluster of size 1. Because if I have an empty graph, this corresponds to Q to the power n, which is what we counted here. Is this clear? So the partition function of the POTS model can be written as a sum over all possible graphs, where each graph is weighted by Q to the power NC, T to the power n. So this particular model is called the random cluster model and has been very useful in, for example, in doing Monte Carlo simulations, very fast algorithms and so on. So it's good to know that such an expansion exists, but from our point of view, it has no map. It doesn't match at all with this expansion here. It's a nice expansion, but doesn't have any resemblance to the low temperature expansion. So we have no duality. Okay, so we need to construct some way. We have to. Is this particular derivation clear? Once you write this way, you can define a model which is a random cluster model where I take a particular configuration and I can put any weight I want for Q. It need not be an integer. And then you can take limits of Q finite, no, Q to any limit you want, Q going to 1, which is not, if I take Q, for example, in the POTS model, I cannot have Q 1, can put 2, 3, 4. But once I make this jump, I can take any limit I want, and you get interesting limits when you take Q going to various limits. Should I mention that? No, because then I would So for example, when you take the limit Q going to 1, you get some well-known model called percolation model. If you take Q going to 0, you get something called some other model. Q going to 0, if you get the, it doesn't matter. But this particular model is important by as he said. But it doesn't match. So we need to ask whether there's a duality between a low temperature expansion and high temperature expansion. Can we construct one? So it turns out you can. So what is it we want? So from the icing model, what we want is that I should be able to generate graphs of the kind, so if I have a particular low temperature expansion like this, I should be able to get a polygon like this. Which is a bit different from the icing polygon because it has now vertices of size 3. Here I should get the other one. I should get a square. So we should be able to generate these sort of squares for some expansion. Okay, so let me try to expand. So what one wants to do is to write e to the power beta Is that clear? We need to construct a high temperature expansion which sort of looks familiar to the low temperature expansion. Okay. So I'm going to write this as, let me just put the notation right. 1 plus, yeah, C of k to 1 plus some t times g of S1, S2. Okay. We'll try to figure out what g of S1, S2 is. Now, and then when you take that, this is first a single expansion. And when you take the product, we get the product like before. But now we want to put some constraint of g on S1, S2. So what is one constraint that comes? So the dual lattice, if I look at it, I can get shapes which have odd number of bonds. 3 can come out, but can I have a site out of which only one bond comes out? Okay, so if I had a low temperature expansion of M1, M2, and I draw the diagram of the dual lattice, I'll get a polygon, the pink polygon. In the pink polygon, if I look at this side and this side, I have now 3 bonds coming out of them. In the square lattice icing model, we had 2 of 4. So that property we have violated. So we have odd number coming out. But there's another odd number is 1, which is like a dangling bond. So for example, how can I draw? So I want to draw the same. So can I construct, for example, some diagram like this in the dual lattice? There's a dangling bond here. Nothing can come out of that. But how do I cannot construct something like this. This corresponds to M1, M2, but this is M2. This is I don't know, M3. But what about this? These two are connected. I cannot go. I can go from here to here. So M1 equal to M2, but then I cannot have a bond here. So I cannot have a dangling bond. Okay. The dangling bond is 1. You cannot have 1 bond coming out. You can have 3 bonds coming out. Is this example okay? Okay. So if I don't want a dangling bond to occur, what I want to have is summation g of S1, S2, sum over S2 should be 0. That's the only way you can do that. So if I had a single bond sitting there and I sum over one of them, it should go to 0. So if I call this spin as S1, there's a summation over S1 happening, and that should give you 0. So we are trying to guess what g of S1, S2 should be. So this should be 0. But g of S1, S2 should be for some function of delta S1, S2. So I'm going to write this as summation A plus B times delta S1, S2 should be 0. sum over S2. That is Q times A plus B should be 0. Or B should be minus Q times A. If this is true, this will be true. So a good choice for G is Q times delta S1, S2 minus 1. So this particular choice happens to work. So if I choose, so let's try to work out with this example a few terms in the expansion of the high TC expansion. So this was just to make us guess what it should be. Okay, so let us look at some properties of G of S1, S2. So first we have shown that summation G of S1, S2 sum over S2 is equal to 0 by construction. Now I'd like to show that summation S2 G of because now a lot of terms are going to come. Like now in our mind we'll have squares, polygons coming. So sums of this kind will come. So we'd like to know how that behaves. What is this? This is Q times minus 1 sum over S2. The first term gives you Q square. Delta S1, S2, delta S2, S3 sum over S2. That is Q square delta S1, S3. The second term is minus Q plus Q. You can check this, which is same as Q times G of S1, S3. So the effect of summing over S2 is to remove it from the summation. Easy to do. It introduces a factor Q, and you can remove it from that sum. Okay. So with this particular thing, let us look at a few examples. So we are not allowed dangling bonds. So what is the minimum? Now we again expand as before. Wherever G of S1, S2 comes, T comes, we put a line between that S1, S2. We are going to expand this in terms of, like we did before, diagrammatically. So now we want to ask what's the smallest diagram that will contribute. The only constraint is that there should be no dangling bond. So what's the smallest diagram? The square, t to the power 4. Okay, so the first term is order t to the power 4. Am I telling too fast? Is it okay? This step is now, we have argued that we are now going to expand this, and then for every expansion we are going to sum over all the spins. And if I have a dangling bond in that spin, it will be 0. Okay, so I'm not allowed a single spin, so I cannot have graphs. So what is the simplest graph? Order T is this one, that is 0. Order T square is 0, because that is this one. T cube is something like this. Okay, like that, not allowed. T to the power 4 I can close. I have a polygon. I can close it. Okay, so order T to the power 4. This one. So it comes as a factor T, 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 T. And what are the other terms that come? So I have T, G of S1, S2, S2, S3. This is my sum over S1, S2, S3. This particular diagram contributes a term of this kind. But when I sum over S2, I get Q. Sum over S3, I get Q. S4 I get Q. So this is Q to the power 4. Where I use this particular expression. That is not true. Sorry, that is not true. What do you get? Summation T to the power 4. I get, when I sum over S2, I get G of S1, S3, G of S3, S4, G of S4, S1. Okay. Now I sum over S3, I get a Q square and G of S1, S4. So now I have G of S1, S4, the whole square, which I should sum. And that answer you should just figure out should be something. This Q square into Q. So this becomes Q to the power 4 into Q minus 1 Q to the power 4. That you should do and see. But this particular term that comes is the same as the low temperature expansion. There's a remaining n minus 4 spins, which when I include, I get Q to the power n into Q minus 1 e to the power 4, which is exactly what you got here. Q to the power 4 n into Q minus 1. So what you should check, you should look at the next diagram, and make sure that they match. So if I look at the next shape, which is a rectangle of size, this one, or if I take a rectangle with a line in between and work out the two, you should be able to get those two terms correctly. Okay, so that is the, so now the mapping is between e to the power minus k and what? And t. What is our t? E to the power k minus 1. What is our t? Yeah, t is e to the power k minus 1. Oh, did I do this? So you have to determine what is t. I have not mentioned what is t. I didn't mention what t is. So you have to just figure out what t is. Sorry, I just went too far. So t is e to the power k minus 1. It's very easy to do. E to the power k minus 1 by e to the power k. So if I equate this to e2 minus k, I get my transition point for Potts model. And that happens to be Kc is log. So I jump many steps because I have no time. Okay. So you get Kc is 1 plus root q. It's very useful to know these results because even when you do numerics, if you know even Tc exactly, then it becomes very easy to do, much more easier than otherwise. It turns out that for the Potts model, even for the disordered system, that we can find Tc by duality, and it becomes really useful. Even though Tc is model dependent, numerically it makes a lot of sense if you know Tc very well. So this is a bit fast, so you fill up the in-between steps, okay, and figure out. Now, the next step was to look at the 2D Ising model and solve it in 2 dimensions. 2D Ising model is in 2 dimensions and solve it exactly. Okay. So there are 2 ways of. So we have done 2 different ways of doing. In 1D we did transfer matrix, but now we did this high temperature, low temperature expansion in terms of polygons. You can generalize both methods to get the solution. Okay. So let us see. Outline the steps required in both the methods and choose one of them. So one is a bit combinatorial and the other one please stop me. It becomes a bit tedious, huh? So we have to stop and. No, no. Oh, this duality argument, now I'm a bit worried. That is true. So this, all of them depend on the fact that there's a single transition. I do. Yeah. I do. Oh, clock models have that? No, clock model has a duality, but ah, so one has to read that up and see. That will be because they have this. Okay, so let us look at d equal to 2D icing. So first, let us see with transfer matrices what one can do. So let's see transfer matrix. So the first thing to do is to look at the 1D icing model. Let's look at it once more. So you had this, so in d equal to 1, your z was e to the power k, s1, s2, plus s2, s3, and so on. What we did was to write a particular term as e to the power k acting on some S1, I don't know how to write. Well, so if we defined T to be this, then we wrote our Z as summation S1 T S2 and so on. The first step is to rewrite this particular T in terms of a polymetrics. So T is e to the power k times I plus 0 what is this? This looks like what? You spend 1.5 hours listening to something in the morning, sigma x. It is e to the power k. Oh, this is e to minus k. Sorry. Plus e to the minus k sigma x, which is the this we like to write as a times e to the power some gamma times sigma x. This looks very much like what we did for something plus SISJ, because sigma x square is 1. All polymetrices, the square of that is 1. So if you write something like this I can expand, which is A into cos hyperbolic, let's call it B plus sigma x. So what we like to find is A and B. This will be useful when you write the, we can, once we do this for the Ising model for one dimension, you can generalize 2D very easily. So what is A and B? A cos hyperbolic B is K, and A minus K. You divide and you tan H B is e to the minus 2K, like in the duality relation. And A is 2 sine hyperbolic 2K, A square. You take the square of this, you take the square of this, subtract, you get that. Therefore, your transfer matrix T is A times e to the power B times sigma x. Okay, that's a 1D transfer matrix. Is that okay? Now we go to 2 dimension. So how do you want to transfer in 2 dimension? So let me draw a line like this. So what is the idea of the transfer matrix? You suppose you have n layers, n sides. In the 1 dimension, you want to add the n plus 1 side, and the T sort of gives you the weight of adding that particular spin there. In 2 dimension, suppose I have 2 layers and I want to add the third side. So you want to ask what is the weight between 2 particular rows. Now my states become, instead of 1 spin, it becomes a row of spins. So let's say there are m of them, 1, 2, 3 up to m. And I'm looking at a particular row. So this particular row is characterized by the spin at this side, this side, this side. The 2 to the power m side, n 2 to the power m possible configurations. And there are 2 to the power m possible configurations here also. So our T will be a 2 to the power m cross 2 to the power m matrix. Okay. And let us denote the spin at a particular side by S1, S2. So I should have the notation here. S1, S2, S3 up to Sm, and S1 prime, S2 prime, S3 prime up to Sm. These are the 2 layers we have. And we want to ask what is the weight of, so what we want to construct is T into some S1 prime, S2 prime, Sm prime. Okay. Suppose, so now there's interaction between spins in the horizontal direction and the vertical direction. So now let us just make a bit of a difference. Let me call this as K2, and this is K1, or K1 and K2. The spins in the vertical direction interact with strength K1, J1, beta times J1 is K1, and K2 in this direction. Suppose K2 was 0. So let's say the limit K2 is 0. What is my transfer matrix? So I have no interactions in the horizontal direction. I have only in the vertical direction. I know my 1D answer, which is this particular answer. So there is no horizontal interaction at all. There are m sides. If there's a single side, only m equal to 1, what is my transfer matrix? Same as the above. There are 2 sides now, side 1 and side 2. Yeah, so if I take T is A into e to the power beta sigma. So I should shall I make it x on the top and 1 for this particular sign. For this one, what do I get? I get 2. So I can put, do I need to put in a different below or on the top? They commute. So I can put either way. So, yeah, so sigma 2 to the power, sigma x2 m. Okay, this is my transfer matrix if I didn't have any horizontal interactions. Now, if I have horizontal interactions, now I switch on K2. So this B is related to K1. This K becomes K1. Now I put on K2, switch on K2. But the interactions that involve K2, do they involve the 2 rows or only 1 row? They just involve 1 row. Okay? So let me just write down a few intermediate steps just to make that particular thing clear. So, so just like we did for this one, let me write this as sum over so let me come back to this one just to make it clear what we'll do. And then the same step becomes, so I now want to introduce a magnetic field 2. So this is plus e to the power h times S1 plus S2 plus S1. So let us introduce a magnetic field also. The reason being that this particular H is like this interaction among a row, because they depend only on the new side that comes. It doesn't depend on the neighboring sides, only the new side that we're adding. Okay, so once you learn how to write this one, you can just figure out how to write for the horizontal interaction. So how do I write this one? So what I can, so there's a summation over S1, S2, Sn. So one way to do this is to write this as summation over S1. I introduce variables, dummy variables S1 prime, S2 prime, and so on. And this is e to the power k S1, S2 prime, e to the power h S2 prime, delta S2 prime, and e to the power k S2 S3 prime. H is a magnetic field. So if you introduce these intermediate spins S2 prime, S3 prime, and so on. Now this we can write as e to the power k, e to the minus k, e to the power k. E to the power h S2 delta S2 S2 prime is a diagonal matrix. This is e to the power h. And then repeated, this raised to the power n. So this h acts only on S2, on the new side being added, and therefore there's a diagonal matrix. You can write it as a diagonal matrix. That is the point. So similarly, if I were to write an expression for S1 prime, S2 prime, and so on, it just depends on, so I want to write something here that gives you e to the power some operator plus so on, which when acting on S1, S2, S3, which when acting on a particular state gives you S1, S2. What is that operator? So what comes here is, now we are going to add the term that comes from the horizontal interactions, which was S1 prime, S2 prime, S2 prime, S3 prime, and so on. What operator which acting on the particular state gives you that particular series, S1 S1 prime, S2 prime. Is the question? So I S1 prime, S2 prime, plus S2 prime, S3 prime, plus so on. Okay. Yeah, if I had take sigma z and act on a particular, I get S1 prime, S2 prime. So if I replace this particular one by e to the power k, summation sigma z I sigma z I plus 1 sum over I generate this particular series. This is diagonal. If I choose a basis in which sigma z is diagonal, this just gives you this particular expression. So my transfer matrix becomes A times e to the power m, e to the power b times sigma 1x plus sigma 2x plus so on, into e to the power k times. Does this look similar? Have you seen this before? No, this particular one transfers from a particular row to the next row, and this one transfers within a row, within one row, but we are adding a row one by one. This particular, the terms here, do they look familiar? What's the difference? So this looks very similar to what Kedar has been doing up to now, the transverse realizing model. What's the difference? So now you want to find the ground state of this largest eigenvalue of this transfer matrix. The transfer realizing model and this, what's the big bit of a difference? One dimension. Now this is one dimension. Once you write, the transfer matrix makes the dimension one dimension lower. You just solve the transverse realizing model in the morning. Okay, so while you think about that, so then once you have, so this is method one. So let me just outline what goes on after this. So once you have a transfer matrix like this, like Kedar told in the morning, sigmas anti-commute on site but commute otherwise. So it becomes a problem. So you can make them something called, you can fermionize by something called a Jordan-Wigner transformation. And follow all the steps which Kedar did, and you can get the free energy for Ising model. You can diagonalize. Okay, so what was the next step? After Jordan-Wigner, what did you do? So he did a few steps, 1, 2, 3, 4, in a certain order. Okay, so so the Hamiltonian, the transfer matrix looks very similar to the transverse realizing model which is solved. And the same steps follow for this one too. Okay. So let's not go, so you think about that. But I want to outline the other solution also, and then we will decide what to do. This is the transfer matrix approach. So what I want to now tell in 5 minutes is combinatorial approach. So the starting point of this one, so we are going to summarize the steps involved in the combinatorial approach. The starting point is the high temperature expansion. Z is 2 to the power n cos 2n into sum over all possible graphs e to the power perimeter of graph. Now, if you could count the right-hand side, if I could count all possible graphs, if I have a formula, so graphs has a restriction, these are closed and even vertices. If I could count the right-hand side, I know the solution. But the trouble is counting. But since Ising model is solvable, this count is possible. So let us see how we can count. So suppose I take a particular, a few graphs that come. No, this is the zero field. We cannot determine. No, that is very difficult. But from this you can get the free energy as well as spin-spin correlation in zero field. You can. So let me look at a few diagrams that come in the expansion. So the first thing to imagine is that these diagrams are created by a trace of some walker. So there is a particular walker which starts here, goes this way, goes this way, goes this way, and comes back to the origin. Or here, you can think of the walker as going from like that. It could go like this and come back to origin. I could have drawn different ways too, but in principle, I can think of these shapes as a trace of a walker. Now, the walker has some constraints. It cannot intersect itself other than at the vertices. It's what is called a self-forwarding, almost a self-forwarding walk. Now, that's very difficult to count. So, if there is one way of converting this to a random walk, are you people familiar with random walk and self-forwarding walk? So, random walk is a walk which starts at the origin, takes one of the 4 neighbors. Every time it comes to a site, takes another 4 neighbors and goes. There's no restriction. It can come back to itself. It's easy to count because there are no constraints. The self-forwarding walk is more difficult to count because once you walk, it knows that it cannot come back to itself again. Therefore, it has infinite memory. It becomes difficult to count. So the original problem has some self-forwarding nature. But if you could make it a random walk, then you could count. But there are many issues. One is the issue of overlap, and the other is the issue of how many ways can you assign a walk to a shape like this. Okay? So for example, a shape like this could have 3 different realizations. One is like this, like that, like this, and another walker goes like that. That is one way. Or I could think of starting like this, going vertically up, coming down, and then I can have a possibility where I go up, I'll turn right, go up. So there are these 2 issues. One is the issue of overlap, and the other is even when there is a single corner overlap, how to assign from a single graph to many walks. So each time the vertex comes, you can have 3 ways of arranging. So there are these 2 issues. So the question is, can you assign a weight for each walk? For example, when it comes and meets at a point, can you assign a weight such that many of them will cancel out? You take a random walk, you put weights appropriately so that when you sum over all the walks, many of them will cancel out and you're left with only the self-forwarding walk. So that's the question. Can you do this or not? So you want to make a problem a random walk problem. So that's a statement. So it turns out that this can be done. So let me now define how the key step in that. So consider all possible random walks on a two-dimensional lattice with one constraint. The constraint is that it cannot turn back. immediately. So I cannot go like this, and come back like that. This is not allowed. But otherwise I can intersect. Okay? But the immediate turn is not allowed. No immediate turn. Okay, so this is not a big constraint because it's a single step memory and you can take care, you should be able to do that, you should be able to calculate with the single step memory. So it's like a random walk still. The second is to assign a weight. So now you consider all possible random walks. So let me consider, this is in 2 dimensions, yes. So let me consider a few random walks, we'll come back to the origin. Okay. Now, for each of these paths, you assign a weight as follows. So every step, you give a weight t. Every time it takes a left, you put a weight e to the power I pi by 4 for left. T for every step anyway. For right, you put e to the power minus I pi by 4. So if it turns left, you say, I know I have taken a left. Right, you know I have taken a right. Remember, these are also local. It doesn't depend on memory. It's an immediate thing. So you can possibly take that into account still. Then you ask, when I come back to the origin, what is my weight? So number of right steps and number of, is there a relation between number of right steps and number of left steps? Equal? But if I look at this one, I get one left turn, one left turn, one left turn. There are 4 this is the first left turn, the second left turn, third left turn, fourth. There are no right steps and left steps are equal, but right turns and left turns are not equal. Okay, so if I look at if I multiply the factors for this one, I get minus I pi by 4, I pi by 4, I get e to the power I pi. If I take this one, I take one left turn, one right turn, that cancels out. One right turn, 2 more right turns, 2 right turns, one left turn, no turns. So this is e to the power 0. So the weight has changed for that one. Okay. So now you should take the 3 examples I drew and find out the weight for each one. One of them will be +1, one of them -1, and one will be -1. 2. So now the rule is you assign to each walk a weight. So weight of a walk P is t to the power length, how many steps you have taken. And the other constraint is that you take these weights, so e to the power I pi by 4 to the power m into -1. So if a continuous state, weight is 1. So there is a factor that comes from e to the power I pi by 4, whatever that may be, into -1. So that the weight of this is 1 and the weight of this is -1 over. This is the weight of a walk. Okay. So is that clear? So you consider all possible random walks with a constraint, you cannot turn back immediately, and you assign weights for each left turn and right turn. Then there is a result. It says, so this is the key result in the derivation. It says summation over all possible graphs e to the power mod g is equal to product over all possible walks with some constraints, which I will tell, 1 plus WP, W. So this is the key step. It says, if I look at the partition function, this particular sum is equal to the product over the weights of each walk, unconstrained walks of this kind, with weighted steps. So this is not very obvious, and it's difficult to show. But what we can do, is to ask whether if this is true, we can try to argue why this is true by looking at simple diagrams. And if this is true, how to go ahead trying to solve the Ising model from that point of view. I initially thought we will solve it using the transfer matrices, but it is exactly what Kedar has done. So I don't want to, what you should do by, you try to understand what he has done and then look at the original, not the very original paper, but original paper. You look at the paper by Lieb, Schulz, Mattis, Review of Modern Physics, I think 1966, about 1966. I think it is not worthwhile trying to do it once more here because I'd like to introduce some commutative methods. This then introduces some commutative methods in solving. Yeah. So you have to, at least a few of you have to, because it makes both the things clear. How to solve the transfer, you understand both the things much better. But you have to work out all those, like when you do Jordan-Wigner, you have to make sure that the commutation relations become correct. All of them become correct, you have to check. It's a bit of tedious work, but please do that. So I change. So what I will do tomorrow is to try to argue why this formula is true, and given that it's true, how to compute the partition function. So you'll learn a bit about how to do generating function for walks and so on. So it will be instructive that way. Okay, is that any questions? In the transversal Ising model, this was a plus this. And I write it like that, if I have e to the power a and e to the power b, can I write it as e to the power a plus b? When can I write it as e to the power a plus b? When it comes. What happened in the Cayley tree in the Bethe lattice? Why don't you tell some answer? Remember, on a finite tree, there are no loops. But that's a Cayley tree. We were not solving on the Cayley tree. So the Cayley tree answer is well defined. Yeah. So it's not very. It's the Bethe limit is a bit tricky. Okay. So here, if you continue the way Kedar described, you take the Jordan-Wigner transformations, you do the Fourier transform, you do the other transformation which you did, Bogoliubov-Latin transformation, then you can find the free energy. Okay. And once you have the free energy, if you differentiate with respect to T, you get the divergence CD. You can find. So then, so at every step you have to ask, if I put sigma I, sigma j, what is the corresponding thing in terms of sigma matrices which you have to compute? That's a bit more complicated. So those, I think, once you're interested, you should do